Have you ever really stopped to think about how we sense the world? I mean, everything from the taste of your morning coffee to the way an aspirin works, it all comes down to these tiny little molecular machines called receptors. They are quite literally our body's connection to reality. But what if the way we've thought about them for decades has been missing a huge piece of the puzzle? Okay, let's get into it.
I want to start with just one number, over 60%. That's how many of our modern medicines are designed specifically to target these receptors. So right away you can see this isn't just some abstract biology. This is at the very heart of our health and medicine today.
And that really is our first big idea. Receptors are, without a doubt, the central target for modern medicine.
So what you're looking at here are the key players in this story, a huge family of receptors called GPCRs. The easiest way to think of them is as these tiny little gatekeepers on the surface of all our cells. And so many drugs, from allergy medicine to antidepressants, their whole job is just to knock on these gates and pass a message inside. When it works, we feel better. But when these gatekeepers malfunction, you get all sorts of diseases.
Now, for a long time, we thought we had a pretty solid understanding of how all this worked. But the closer we looked, the more we started to find some pretty serious cracks in that foundation.
The classic model is actually really simple, super intuitive. You can picture it like a volume knob. You add a little bit of a drug, it binds to the receptor, you get a little bit of a response. You add more drug, you crank up the volume, and you get a bigger response. It's a nice, clean, proportional relationship. Makes perfect sense, right? But what if that beautiful, simple picture is actually hiding what's really going on? What if it's just wrong? Because scientists kept running into these bizarre little paradoxes that the volume knob idea just couldn't explain. Things like, why does a drug's effects sometimes just fade away, even when the drug is still right there? Or even weirder, how can some receptors be switched on when there's no drug around at all? The old model just hits a wall with these questions.
And to get past that wall, to solve those paradoxes, it took a completely new way of looking at the problem. A total change in perspective that we're calling the absolute shift.
Okay, now this is the whole game right here. The old model always asked what fraction of our receptors are active, what percentage are turned on. The new model asks a totally different question. What is the absolute net shift, the actual raw number of receptors that we've pushed from inactive to active compared to where we started? It's a subtle change, but it's everything. We're moving from thinking about percentages to thinking about absolute numbers.
And this is the core of the net shift model. It says that receptors aren't just sitting there in the off position waiting for a drug. No, they're in a constant state of flux, a delicate dance or equilibrium between active and inactive states, all on their own. A drug doesn't flip a switch. It just perturbs that balance. It nudges the equilibrium one way or the other. And that nudge, that net change in numbers, that is the signal. Okay, so we've got this new model. But the real test, right, is can it actually solve those weird puzzles that stumped the old one? Let's find out.
First on the list, let's go after that desensitization puzzle. Remember that one, where adding more of a drug can somehow lead to less of an effect? How on earth does that work?
And here is the absolutely beautiful solution. That weird bell-shaped curve you see on the left, the one that was a total anomaly for the old model, well, it turns out it's an inherent prediction of the net shift model's math. As you pour in more and more drug, you eventually start to saturate not just the active state, but the inactive state too, which actually starts to pull the whole equilibrium back the other way, reducing the net shift. The paradox just evaporates. It's not a paradox at all.
Okay, next up, the mystery of spare receptors. Why don't we need to activate every single one of them to get the biggest possible response?
And again, the answer is all in that absolute shift. A cell's internal machinery, the stuff that actually does the work, it has a limited capacity. So it doesn't need 100% of its receptors screaming at it to get the message. It just needs a large enough absolute number of them to shift into the active state. And that's enough to completely max out the system. Any receptors beyond that number are, effectively, spare. So this new model does more than just solve old problems. It's actually opening up brand new possibilities. And it's revealing this much deeper, more profound connection between the molecules inside us and the way we experience the world.
And this is not just theory. This is having a huge real-world impact. Using the net shift model, scientists can now engineer drug combinations that basically prevent that desensitization from happening.
Just look at this graph from a cardiac study. The dotted line is the drug by itself. You see that classic peak and then fade. The solid line, that's the combination designed with the model, a stable, powerful, non-fading response. This is how you design smarter, safer medicine.
But the story gets even bigger. Way back in 1923, researchers noticed something strange about adrenaline. They saw that its effect on blood pressure wasn't a straight line. It followed a logarithmic relationship, which is the exact same rule from psychology that describes how we perceive things like the brightness of a light or the loudness of a sound. It's called the Weber-Fechner law.
And here is the absolute kicker. The mathematical equations that fall out of the net shift model naturally produce that exact same logarithmic relationship. I mean, think about what that means. The fundamental math that governs how our receptors behave at a molecular level appears to be the very same math that governs our conscious perception of the world.
And that leads to this final, really profound thought. What if this simple chemical equilibrium, this dance between just two states, was the chemical spark that allowed life to start sensing its environment in the first place? It suggests that our ability to see, to hear, to feel, maybe even consciousness itself, is an emergent property, something built from the networked responses of countless trillions of these tiny molecular shifts happening every single moment. We aren't just beings that have chemistry. We are sentient beings made of chemistry, born from the universe's fundamental drive for balance.